For years, artificial intelligence has operated inside a very specific cage. You open a browser, type into a text box, and wait for a conversational reply. The intelligence was there, but it remained physically walled off from the actual work. Systemic agency is the missing link between talking and doing. While a model can generate a list of instructions for a human to follow, it traditionally stops at the edge of the chat window, unable to bridge the gap between the code it writes and the icons on your desktop. The GPT 5.5 architecture, deployed through OpenAI's Codex desktop app, removes this separation by operating natively inside the local environment. Instead of acting as a passive advisor, it takes direct control of the mouse and keyboard. It opens your files, navigates your folders, and performs the keystrokes itself. This transition suggests that the value of an AI is no longer found in its ability to hold a conversation, but in its ability to access and manipulate the digital environment. To observe these baseline capabilities, we can look at a controlled field test. The prompt asks the system to build a financial waterfall analysis, a complex spreadsheet used to calculate payout structures when a startup exits. The model does not output a block of Python code or a static text representation. It directly opens Microsoft Excel and begins constructing a live, editable file. It pulls key variables from a provided template, maps out the cells, and wires up the dependent formulas across the document. Midway through the build, the system realizes its calculation for the employee options pool is mathematically incorrect based on its current trajectory. Rather than pushing forward and delivering a broken file, the execution halts. It isolates the flawed logic, corrects the options formula independently, and finishes building the model. The user never intervenes. This behavior proves an active comprehension of the live digital environment. It is reading the state of the application and adjusting in real time. That environmental awareness scales up when the tasks require moving between entirely different programs. Given a 2-sentence prompt to document recent software releases, the agent autonomously launches Google Chrome. It navigates to the corporate domain, locates the product updates page, and reads through every individual release note listed. After gathering the raw information, it moves directly into Apple Notes. It creates a new file, drafts a structured summary with bullet points, and attaches the source URLs at the bottom. There is no back-end API connection configured here. No custom Chrome extension or specialized plugin bridges the two programs. The operating system itself has become a natively readable interface for the model, allowing it to use desktop applications like a human employee would. The architecture's ceiling is tested when you deploy it for unsupervised, long-duration work. We tasked it with a 9-hour overnight objective: build a complete desktop application that tracks live audience engagement metrics across YouTube, Instagram, X, and a newsletter. Left in full auto mode, the agent spent its first 2 hours driving the local browser to solve Meta's platform authentication protocols on its own. It wired up the necessary developer keys and began extracting live view counts, follower data, and relationship indexes from all 4 distinct digital platforms. During the build, Instagram's server rejected the agent's token request. In standard software development, an unhandled rejection crashes the script. Here, the system logged the error and autonomously pivoted to pull cached data from its own archive so the execution could continue. It then wired in an open-source routing system and integrated a local device-based language model to safely draft responses to incoming audience comments. By morning, a functional multi-tab analytics operating system was live on the machine. 0 lines of code were typed by a human. These field tests align with the quantitative performance data verifying this architectural leap. The clearest indicator is a benchmark testing multi-step professional knowledge work across 44 different industries. This chart shows the performance distribution among top-tier models on complex multi-step tasks. While legacy competitors cluster near the median, the new architecture reaches a performance score of 84.9%, the highest recorded on this specific test. The mechanical advantage driving this score is efficiency. The model requires significantly fewer tokens to execute a task, compressing its actions while utilizing a massive expansion of long context memory to keep track of every moving piece. The data suggests this system is engineered for messy, overlapping, systemic execution, rather than solving isolated logic puzzles in a vacuum. The digital landscape has split. On one side are legacy models built to edit isolated files of code or write text. On the other side is an architecture built to manage entire operational systems. The immediate consequence for the digital economy is the removal of the middleman. Human operators no longer need to manually guide workflows, fix syntax errors, or shuttle data between tabs. The relationship between user and computer is inverting. We are moving away from a reality where humans use tools into one where tools operate the system on our behalf. Building software is transitioning from manual engineering to high-level delegation. You define the objective, set the parameters, and leave the machine to execute the intent. Artificial intelligence has crossed the threshold of digital dependency. It is no longer reliant on us to click the mouse. In the execution layer of the digital economy, the operator is now optional.